Linear attention replaces the unbounded key-value cache of softmax attention with a fixed-size recurrent state. That gives you linear time training and constant memory decoding. The hard part isn't what to forget, it's how to edit this compressed state without scrambling existing associations. Delta rule models like DeltaNet subtract the current read before writing. KDA sharpens forgetting to be channel-wise. But the active edit still uses one scalar gate for two unrelated jobs: how much to erase on the key side and how much to write on the value side. Gated DeltaNet-2 from NV Labs decouples these. Start with the recurrence. At position t we have query q sub t, key k sub t, value v sub t. The model maintains a matrix state S sub t, shape d sub k by d sub v. The update is just an additive outer product, S sub t equals S sub t minus 1, plus k sub t times v sub t transpose. The read is one matrix vector product, O sub t equals S sub t transpose times q sub t. Expanding over a length L sequence gives the familiar causal matrix form, O equals qk transpose, elementwise times the causal mask, times v. Fixed size state. Linear time. Every outer product just adds nothing is ever removed. For efficient training, the sequence is split into chunks of size c. For chunk n, let q sub n, k sub n, v sub n be the query, key, value blocks. Let S sub n be the state at the start of the chunk. The partial expansion is S sub n plus 1 equals S sub n plus k sub n transpose times v sub n. The output block is q sub n times S sub n plus q sub n times k sub n transpose, elementwise times the in-chunk mask m sub c times v sub n. The recurrence only crosses chunk boundaries inside a chunk. Everything is matrix multiplication. Tensor core friendly. First fix, forgetting. Mamba-2 adds a data-dependent scalar decay before each write. S sub t equals alpha sub t times S sub t minus 1 plus k sub t times v sub t transpose. With alpha sub t in 0, 1, the state shrinks every step. If gamma sub t is the cumulative product of alphas, each earlier write is read at time t with factor gamma sub t over gamma sub I. That yields a decay-aware attention mask and preserves the chunkwise structure. But it's a single scalar, it decays the entire state uniformly. Second fix, targeted editing. DeltaNet reads the value currently associated with the new key and subtracts that before writing. The update is S sub t equals S sub t minus 1 plus beta sub t times k sub t times v sub t minus S sub t minus 1 transpose times k sub t, all transposed. Equivalently, S sub t equals I minus beta sub t times k sub t transpose times S sub t minus 1 plus beta sub t times k sub t v sub t transpose. With key norm equal to 1 and beta equal to 1, the matrix kk transpose is a projector, it overwrites the association at that key. Beta equal to 0 leaves it untouched. This is one online gradient step on the local regression loss, 1/2 of S transpose k minus v squared. Gated DeltaNet combines both, a scalar decay alpha sub t plus the delta rule edit with scalar beta sub t. S sub t equals alpha sub t times I minus beta times kk transpose times S plus beta times kv transpose. KD, a Kimmy delta attention, sharpens this by making the decay channel-wise. The scalar alpha becomes a vector. With d sub t equals diag of alpha sub t, the update becomes S sub t equals I minus beta times kk transpose times d sub t times S sub t minus 1 plus beta times kv transpose. Each key channel can now forget at its own rate. Big jump. But notice, beta sub t is still a single scalar. It controls both the erase and the write. Here's the bottleneck. In every model up to KDA, the active edit uses one number beta sub t to control two unrelated decisions on every token. Decision 1 lives on the key side, which coordinates of the cached read should be removed. Decision 2 lives on the value side, which coordinates of the incoming value should be committed. Erasing is a key side operation. Writing is a value side operation. There is no a priori reason these should share strength. Treating both as one scalar is a modeling restriction, not a requirement of the delta rule. Gated DeltaNet-2 attacks exactly this tie. Gated DeltaNet-2 splits beta into two gates. A channel-wise erase gate B sub t lives in 0,1 to the D sub k, one entry per key channel. A channel-wise write gate W sub t lives in 0,1 to the D sub v, one entry per value channel. Define the gated key, E sub t equals B sub t element-wise times K sub t. And the gated value, Z sub t equals W sub t element-wise times V sub t. The erase gate weights which key coordinates participate in reading the old content. The write gate weights which value coordinates land in the state. Both come from separate linear projections of the token, followed by sigmoid. Apply the channel-wise decay first. Let S tilde sub t equal D sub t times S sub t minus 1. Read the gated direction, R sub t equals S tilde sub t transpose times E sub t. Then write the gated residual, S sub t equals S tilde sub t plus K sub t times Z sub t minus R sub t transpose. Putting it all in one line equation 10 in the paper, the boxed expression S sub t equals I minus K sub t times open paren B sub t element-wise times K sub t close paren, transposed, all times D sub t times S sub t minus 1, plus K sub t times open paren W sub t element-wise times V sub t close paren transposed. The left factor of the erase matrix is still K sub t that preserves the right direction of the delta rule. The right factor becomes B element-wise K channel selective on the read. The right term becomes K times Z channel selective on the value. Gated delta rule 2 is a strict generalization. If you set B sub t equals beta sub t times the all ones vector of size D sub k, and W sub t equals beta sub t times the all ones vector of size D sub v, both gates collapse to the same scalar, you recover KDA exactly. If on top of that you also collapse the channel-wise alpha back to a scalar, you recover the original gated delta net. The model preserves the known scalar-gated updates as tied subspaces, and learns outside those subspaces only when erase and write actually want different channel structure. Gated delta rule 2 is also the closed-form solution of a small online optimization. The local objective at step t is L of S equals 1/2 S minus S tilde squared Frobenius minus 2 times the inner product of S transpose K with Z minus S tilde transpose E. Setting the gradient with respect to S to 0 gives S sub t equals S tilde plus K times open paren Z minus S tilde transpose E close paren transpose. That's exactly equation 10. Reading, the new state stays close to the decayed memory while applying one associative edit whose residual compares the gated write target against the content read along the gated erase direction. 1. Gate-aware gradient step. Implementation detail on the channel-wise decay. Following gated DeltaNet, the log decay tensor is G sub t equals minus e of a element-wise times softplus of W sub f times x sub t plus delta. Then alpha sub t equals exp of G sub t a vector in 0,1 to the D sub k. In practice, this is computed in FP32 before the CUD a kernel consumes it, avoiding precision loss in the cumulative log decay sum. The erase gate B can optionally be scaled into 0,2 for a negative eigenvalue variant. Training stays chunkwise. Inside a chunk, define the cumulative log decay G sub r equals sum from I equals 1 to r of G sub I, and gamma sub r equals exp of G sub r. Define a decay normalized state S hat sub r by S sub r equals diag of gamma sub r times S hat sub r. The channel-wise decay is absorbed into each rank 1 erase, bar K sub r equals gamma sub r to the minus 1, element-wise times K sub r, and bar E sub r equals gamma sub r element-wise times E sub r. Stack rows into matrices, bar E equals gamma element-wise times open paren B element-wise K close paren, and Z equals W element-wise V. Build the strictly lower triangular matrix T equals trill of bar E times K transpose with -1 diagonal offset. Then A equals I plus T inverse, computed by a small forward substitution. The WY auxiliaries are Y equals a times bar E and U equals a times Z. End of chunk state and output match KDA's chunk equations exactly. Triangular solve plus dense matmul tensor cores. Here is the actual block design from the paper. On the left, the hybrid stack repeats n times gated DeltaNet-2, MLP, sliding window attention, MLP. Residuals between each. On the right, the GDN2 block. Query and key paths use linear projection, short causal convolution, CLU, and L2 normalization for stability. The value path uses linear projection, short conv, and CLU. The central recurrent operator is Gated Delta Rule 2. The decay branch produces alpha from the log decay projection. Channel-wise erase B and write W each come from one linear projection followed by sigmoid. Output is RMS normalized multiplied by a CLU output gate projected back. Two model families are trained. The recurrent family stacks gated DeltaNet-2 mixers under standard MLPs. The hybrid family inserts sliding window attention after every recurrent mixer. The cell becomes GDN2, MLP, SWA, MLP. The recurrent mixer compresses long history into constant memory. The SWA handles short shifts, comparisons, and local retrieval inside a fixed window. With a fixed window, the hybrid keeps linear sequence scaling overall while gaining a small bounded exact attention cache. At 1.3B parameters trained on 100B tokens of fine web edu with a 4K training length and matched recipe, the recurrent gated DeltaNet-2 hits wiki text perplexity 15.90, the best among Mamba-2, Gated DeltaNet, KDA, Mamba-3 SISO, and Mamba-3 MIMO. Lambda perplexity 11.41, also best. Average common sense accuracy across Pika, HelaSwag, Winogrand, ARC, OpKey, Sika, and BoolQ comes out to 53.11. With sliding window attention in the hybrid setting, perplexity drops further to 15.62 and average accuracy rises to 53.97. Where gated DeltaNet-2 shines, long context retrieval. On the ruler benchmark single needle in a haystack and multi-key needle in a haystack at 4K tokens, recurrent GDN2 hits 93 on SNIA2, 89.8 on SNIA3, and 37.8 on the harder MKNIA1 setting. For comparison, KDA scores 30.6 on MKNIA1, gated DeltaNet only 27.8, Mamba-2 21.4. The gap widens exactly where the recurrent state has to keep many competing associations separate. That is the point of decoupled erase and write. Cost of the extra gates. Figure 2 of the paper reports single H100 training throughput for the hybrid 1.3B models, varying sequence length at a fixed token budget. Gated DeltaNet-2 stays nearly flat, 38 kilotokens per second at 2K times 8 batch, dropping only to 36.1 at 16K times 1. Transformer drops sharply over the same range. Relative to KDA, GDN2 pays a small constant gap for the extra channel-wise erase and write gates. The flat scaling profile of recurrent mixers is preserved. To recap, channel-wise erase gate B on the key side, channel-wise write gate W on the value side, KDA and gated DeltaNet recovered as collapsed cases, Chunkwise WY form still tensor core friendly, and the best recurrent model at 1.3B on fine web edu with the biggest gains on long context retrieval. Code is at github.com/nvlabs/gateddeltanet2. If the bottleneck of fixed-state recurrence really is interference among compressed associations, then decoupling erase from write is the right axis to pull on.